Hello? Hello?
Good
Yes,
evening.
sir.
Good
Good
evening.
evening, sir.
So who is the coordinator now?
Shanmugraj from TV School, sir, Madurai.
Okay. You are going to coordinate the question answer session? Who is going to? There is normally somebody will be there. Google is not there. Then Kabilan. Kaliradi. How many of you are there? 140 students are joined. 140 participants. So shall we start? Google has come.
Sir, good evening, sir.
Good evening. Good evening. So congratulations for a very good flight.
Yes, sir. Yes, sir. Thank you, sir. Thank you, sir.
You
It's
put
the
the
one that-
satellite in the correct place.
Yes, sir.
Is
We
it,
have even,
it is working now? Started?
it will take 20 days, sir. The deployment of the radar. So NASA has informed that 20 days it will take, sir. For one step by step, they will be increasing the radar. The opening of the radar has to happen, sir. So after 20 days, complete satellite will be on function, sir.
But health of the satellite is okay?
It is good, sir.
Okay, right.
Immediately solar deployment has happened, sir. That was fine. So now that aperture radar, synthetic aperture radar will be opening up, sir. And that is the costliest satellite in the world now.
Yeah. 4,000 crore.
Yes, sir. $1.5 billion US, they said, sir. So we were like, even Americans were reluctant to give cryogenic. Now their own satellite we have launched, sir, with our own indigenous cryogenic.
Correct. Very good.
Yes, sir.
We are teaching lesson to them. Trump is teaching lesson to us now.
That is the geopolitics, sir.
So shall we start? Or you
Yes,
want
sir.
to wait?
Yes, sir. Yes, sir. Yes,
We
sir.
can start.
Balmurugan has come.
Yes, sir.
Okay.
We can start.
Everyone was waiting for 6 o'clock correct this time.
So, initiate, sir. Very good evening to all present here. So today we are having our session 4 from our Dr. Pillai, sir. So it is the launch center of the world, that is design methodology of the rocket. So very importantly, I think 3 sessions we have completed successfully and 4th session has been there. So again, I request students to interact more with sir, listen carefully, and don't repeat the same questions whoever asked, so that you can able to give up a good question to sir, so that sir can clarify. So without delaying, I like to welcome our Sivathanu Pillai, sir, who is the founder CEO of BrahMos, as well as Guru and Padma Bhushan Padma Shri, for the 4th session conducted on the rocket science. So it's over to you, sir. Thank you, sir.
Okay. Right. Last time we saw about the propulsion system, which is very important for the rocket to go up. And different types of propulsion we have seen. And also the advanced propulsion, to some extent we have seen. We are going to have one more class on the propulsion later. But now, when we talk about the rocket launching, very important factor is the launch center. And how you configure the rocket is also very important. So I thought that it is the right time now to talk about the launch centers of the world, their importance, how it affects the launching, how it affects the performance of the rocket. We want to see that. And also I will show some flow diagrams which will give you an idea how a rocket is designed. So when you say rocket, that rocket has got propulsion, which we have seen, propulsion system. It has got solid or liquid or cryogenic or ramjet or scramjet. All those things are there. But here I am showing a liquid engine. It has got a fuel oxidizer, storage, pumps, then combustion chamber, injector, and flow systems all involved. in making a liquid engine. So all this propulsion is contained in a structure. And without a structure, you cannot hold it. So you need an airframe, and you need the fairings at the top to cover the satellite. Then you have to protect the whole thing. Well, environmentally it should be protected because it is going through a heat affected zone. So you have to carefully cover it with a protection system. And there are support structures connecting the stages. These are all important in the structure. Propulsion structure, but how do you make it working? You need power. So power storage, power conditioning, power transfer from the equipment bay to the bottom of the rocket, all these diagrams. So there's a wire, some few kilometers. Nearly one rocket has got 20 kilometers of wire. So such a connectivity is required to link all the sensors, and then also the assembly of the subsystems you need to connect and give power. Now the rocket has to go in a proper trajectory. The control of the trajectory and guiding it towards the to the goal is done by the guidance and control system. Guidance control system, there are multiple controls are there, thrust vectoring control, then control surfaces like fins, reaction control systems. These are there as control systems, which we will discuss. Then you've got a guidance system. Guidance system is called inertial navigation guidance. This has got sensors which will give the position of the rocket. So these are important along with other sensors for measurement. And there is a very important thing, the brain. Brain of the rocket is called onboard computer. So like a human being, rocket has got the blood flow, that is a propulsion. Structure, you have got the muscles and that whole system which is completely making the body properly. Then you have got the to control, you have got the movement systems, that is your direction movement. The sensors are eyes and then brain, ear, all these are sensors. Like that, the rocket also has got all the things. Now, what for we are launching? We are carrying a satellite. The satellite systems are various mission payloads. This we need, and it has to be interfaced with the launch vehicle. So satellite and launch vehicle are interfaced to work together, and finally the satellite is injected in a particular orbit. So all these things have to be communicated to the ground. So we have got communication system, which we call it as telemetry. Telemetry means you need antenna. Through antenna only you can transmit the data. So the telemetry system, which is measuring all parameters through the onboard computer, uses the antenna to transmit the data to the ground. So then there's a command center. That command center, all the data goes to the command center. Command center has got computer, data processing, data storage, data distribution, and real-time display of the result that you need. So that is called the command control stations. You have got mission control, you have got data control, all these stations are there. This will communicate, bring in all the data from the various telemetry, telecommand, then radars, all the stations abroad, all that the link will be controlled by this command control center. Then if it is to re-enter, suppose you want to recover re-entry or manned mission, you have to re-enter the Shukla re-entered, from when he came down from the International Space Station. So re-entry system, which has got a speed braking, thermal protection, and also the parachute systems is there, that is landing system. So these are important for manned flight, parachute, damping systems, and if it is something wrong with the rocket, then you need emergency systems. All these constitute the rocket. Okay. If you look at a rocket like GSLV, Geosynchronous Launch Vehicle, you've got a big booster. You have seen that launch I showed you. The booster is a solid rocket motor. We have studied about the solid rocket motor. This is a solid rocket motor which has got 139 tons. Yes, 129 means 129 tons of propellant is loaded in this Now they have got 200 tons actually. Now the new booster is 200 tons. Then it has got 4 strap-ons to give the necessary thrust. These are liquid stages. L40 we call it. That means 40 tons of propellant they have got each one. And there are 4 numbers. So they give about 60 ton thrust each one. So that means 240 ton that gives. This gives about 400 tons. So you will see a huge capacity is built here at a takeoff. Then this is second stage is again a liquid stage with 37.5 ton propellant. And this liquid propellant is UDMH N2O4. Here it is a solid is called solid propellants or ammonium perchlorate, that is the oxidizer. Fuel is the aluminum powder. And also there is a polymer. Polymer is HTBB, hydroxyl terminated polybutadiene. So this is the combination for a solid motor, which is thick, solid. Finally you cast it and then put it. Here you are only storing in oxidizer tank and the fuel tank. There are separate tanks. You carry UDMH and N2O4. At the time when you ignite, these two go down through the turbine and finally thermopump, and then they are coming to the combustion chamber, and the ignition, the exhaust comes through the engine nozzle. This is called thrust chamber, and these are the engine nozzle. So this is the second stage. Now you see in between first stage and second stage, you need a connecting stage. That's called interstage. The interstage is between first and second stage. Similarly, second stage to third stage, you need another interstage. These are the connecting thing. So when the launch is going, this burns, and once the burning is over, you have to remove it. But while removing, you need a thrust to take place. So you ignite first the second stage, get the speed, and then separate them so that they don't hit, because this is moving faster. This has no thrust, so you will be moving faster and this will go down. Similarly, third stage, which is the cryogenic here, it is a liquid oxygen and liquid hydrogen. Oxygen is oxidizer, hydrogen is the fuel. So this is a high energy system called cryogenic stage, and we have got the 12 ton thrust in this state configuration. Then you have got the very important thing called equipment bay. This is the brain of the, like our brain, this is the brain of the rocket, where you have got the onboard computer, you have got various controls, the INS, inertial navigation system, and you have got the gyros, accelerometers, many other systems which will give you the position update and control. The whole thing is controlled by the brain. And above that is the satellite, covered by the fairings. So now you will understand what is a rocket. So rocket, what are the systems in the rocket, and then how they are assembled, Why different stages are required? For velocity addition. You cannot give a whole velocity from one stage, you cannot give. Then the stage will be so big and the rocket will be so big, and you are carrying unnecessarily the weight. So that is why stagings are done, so that once the velocity is given by the first stage, it may be 2 kilometer per second speed. But you need ultimately you need more. You need say 9 kilometer per second speed. You want each one stage gives the required velocity to finally to the satellite when it is separated. So this is the configuration of a rocket. Okay. Now this we have seen how the solid rocket is made. You are seeing 2 solid rockets here, 2 white, what you are saying. These are the largest solid rocket motor ever made. Each one 500 tons of propellant. Each one. This is a space shuttle rockets. Once the rocket ignites, then the space shuttle goes up. So this this type of rockets, how the rockets are made, you have got a propellant, which I explained to you already. This is a solid rocket motor. Propellant. Propellant has got a configuration. Particular configuration is based on the thrust time curve you need, igniter and the nozzle. Now the all exhaust comes here. They converge with high speed, and with the speed, high speed pressure, high pressure and high speed is obtained by the divergence. Okay. Now, this is what I discussed with you. There's the blue thing, what you are saying is the 500 ton for the space shuttle, and it consists of 4 parts. Each one you cannot make such a long, multi-story building. You cannot just make. You have to make it by stages. So this has got 4 different parts, and each one has got a different configuration of the propellant inside. If you see this and these are different, these two are same. This is again different. So you can see that configuration of the grain inside, the shape of the configuration is quite different. So this how it is made. This forward segment is the segment which is in the front. Then center segment and 2 are there. And then after means behind. This is the bottom one, which has got the nozzle here, the nozzle. Top one has got the igniter. Okay. Now the shape which I told you, this is the type of shape which has got. It needs some time of thrust like this. A very peak and then comes down, and when it burns, it is a very low thrust. This is the type of configuration which will give this type of thrust. But if you normally what we use is called M type. But we use it like this. We use like this. You have seen that normally our motors are this type, called here it is 6-star configuration. That means 6 lobes will be there. And uniformly, this whole propellant burns radially. The propellant burns radially and gives a thrust. You can see the thrust. Very takes off quickly. It goes, builds up the pressure, and the pressure is constant. And then pressure taps off, and the firing is over. So if you want a different type of pressure, you want very high at the time, or thrust you want very high at the time, then you have to go for this type of configuration, like that. So depending on the mission, what type of thrust you have to impart to the launch vehicle, you have to design the configuration of the grain, propellant grain. This is possible only in the solid. In liquid, you cannot do anything like that. That is flowing. But here you can make it in a different way for different purpose. In the case of missile application, these type of grains are very, very useful. But generally for rocket, is the number 3 is the one which is preferred, which is called M type car. And this also is 2 also is very close to that. This is called propellant grain design. Once you have got the grain design, you have to make the same grain, you have to make it. This you see that grain size inside. So this is the type of, this is the propellant, and you are making the shape. So what you have to do, to get the shape, you need something to go inside. That is called mandrel. So first you have to make a chamber. This is a rocket motor chamber. Then line it. Here is the insulator. You can see the insulation. The brown color is insulation. Once it is made, it is taken to the casting pit. Casting pit is like this. This is the casting pit where you keep the motor vertically down, and then you have to insert the mandrel. You'll go at the center, and then you have to do the propellant flows from here. So before that, you have to make the paste. You have to make propellant paste. These are the making. This is called the slurry making. So make the slurry, and then this is the hopper where you pour it, and through that you pour it down to that. So you have to build it quickly. You have to build it before it solidifies. So the viscosity is very, very important. So you have to make the thing flowing, and the mandrel is at the center, which will give the shape. Then you have to cure it. You have got an oven. This is the oven where you transfer this and cure that. For nearly 20 days it takes to cure. Once the curing is done, it becomes a solid like this. Then you have to machine the shape. You have to machine it at the end and make it ready for for further purpose, further action, assembly. So Mr. Vogel, who is here now, he is in charge of these operations in Sriharikota, where the big rocket motors are given to him. then he will get this done, and then finally get the casting done, and he delivers the solid rocket motor for launching PSLV or GSLV or the big rocket strap-ons to the Mark 3, that is the Mark 3 rocket, big rockets. Okay. But the important thing is the structure also is important. So this is the structure, what you see, this is a steel structure. We normally use the managing steel, which is a special steel with high strength and low carbon alloy. This is a very important material which can withstand the high pressure. The solid rocket motors operate at very high pressure. So you need strength you need for the material. So this is a steel material which is used rolled and welded. It is welded in the industry. This is not done by ISRO. It is done by industry, where they make this chamber. So you can see this chamber. This is another steel chamber. This is another steel chamber. We are also using composite material. This is steel material for the boost stage. For the upper stage, we use composite material. You can see this is called Kevlar motor. Motor case is a composite material. The winding is going on, the winding process to take the shape. And this is used as the third stage of the PSLV. You can see this is a composite material, you can see. So then this is the composite motor. You can see the motor. What is wound here, it has become a motor. Then propellant has been put inside, nozzle has been assembled, and the satellite is assembled. So these are the type of things we do it. Now I go to the control side. Control side means there are different types of controls are there. Why control? You need a trajectory to be shaped. A particular trajectory, you have to put that the rocket should move to reach the required altitude, required position it has to go. So the control is done by different means. This control is called movable fins. These fins can be moved. How fins can be moved? Fin which is there now can be moved by an actuator. It can move. The fin can be moved. And there's a fin tip is also there. Fin tip also can move. There is a control. Here it is only movable fins. So when you move the fin, it is operating in the center of pressure. You have learned that center of mass should be in the forward. Center of pressure should be at the bottom. We have seen for stability. So here, this is the force acting because of the movement of the fin. If you give a movement which is going and the control of the center of the movement is going to be above the center of mass, the rocket will immediately tumble. So you have to do that. Okay, this is moving the fin. Laterally you can move it. So there are 4 fins. If you move the fin, it is like, how do you move it? It is a center point is there. It moves up and down. It is moved. So by movement, you can get the pitch direction, yaw direction, and from the alternate fins, you can get the roll also. So 3 directions you have to move. When you say a control is done in 3 axes. One axis is called pitch axis. Pitch is, if you want to turn it right, it is called pitch. When you want to turn it towards you, it is called yaw. When you want to roll it, when you do the rolling, that is shifting it, then it's called roll. So pitch, yaw, roll, these are the 3 important things which are the directions for applying the control force to make the rocket to go. For example, when we have seen the rocket, it was turning. You can see that in the flight when it is going, it is turning. The turning is done by these fins, they turn. Fins, by movement of the fins, you can turn it to do that. Second thing is called gimbal. You have got an engine which can be moved. Engine can be moved. For example, this is what you see, this rocket. This is Prithvi. Prithvi is a missile, what we are having in India. This Prithvi missile has got 2 engines. You can see 2 engines. By 2 engines operating one direction, you can give pitch. Opposite this direction, you can give yaw. And when they roll, if they operate in two different directions, then roll can be given. This is the biggest advantage of having two fins, two engines. This is called gimballing of the engine. Third type of thing is called vernier. So you can have attached small rockets. And firing the small rockets, number of them will be there. You can make the direction of the movement. Then thrust. This is thrust. Thrust vane. You can see the bottom. There are two projecting things. These are called the vanes. By through the vanes, by movement of the vanes, you can change the direction of the rocket. You can do that. So this is called thrust vector control. And there's one more thing is there. Instead of vanes, you can have the fuel which is flowing at the nozzle of the rocket. You can have a jet. So you have to attach another small rocket which is carrying some other propellant, and then you fire that, you make the flow to happen inside the nozzle. Then also the direction can be changed. That is also called thrust vector control. So these are the different types of controls which you can employ in a rocket. So what I explained to you, one is called pitch, the direction. We want to move it like this. This axis is pitch. Movement towards using this axis is called pitch. Movement against this axis is called yaw. Roll is you roll the rocket. All these things are done at the center of, when you do all these operations, it will be from the center of mass. The movement will be from the center of mass, but the control will be center of pressure, which is somewhere here. Okay. Now you see another one, gimballing. What I told you, gimballing, the nozzle is moved, the engine is moved. This engine is moved by an actuator. So it is there's a thrust frame where the engine is kept, and then the thrust frame is actuated by the hydraulic actuator, which can move the different direction. So if you move this way, the rocket will go other side. If you move that one, it will go here, opposite. So this is the possible. This is a fin movement also. You can see the fin movement of the fin. You change the direction. So here you can see the thrust jet vane. Vanes, which I told you, these are the vanes which control the flow. So these are the mechanisms which we have got. For example, you got a launch. This rocket is launched. It is launched vertically. Now you have to change the direction of the launch, because it cannot be vertical. Then it is a launch from a ship. You go vertical and it comes down, the ship will go. So you have to take it out of the ship from the dangerous zone. So what you do? You have to do a pitching. So when it moves like this and you change the direction of that, it goes like that. Then you need to correct it in the azimuth. Then this is the azimuth plane. You are changing the rocket in the yaw plane. Then it will go in this. If you want to do it in pitch plane, the rocket will go up like this. Why we have to do it? In the case of a ballistic missile like Prithvi, normally physics says you launch with your propulsion, your rocket will go up, and once the propulsion is over, it will come back in a parabolic trajectory. This is what all others are doing in the world. Only in India, what we are doing, we do a pitch control to move it like this. And the force is over. Now you have to maneuver it. We have got a maneuverable wings it has got. So through that, we do that maneuverability. Similarly, you want to do that yaw control. Easily you can do using the two engines. You do the yaw control and then make it steady to reach that point. So this is to avoid enemy to launch a missile to attack our missile. So this whole thing, this type of concept came from India. Our people have found out this maneuverable trajectory will be the best suited for avoiding enemies intercepting our missile. Okay, so I am explaining to you what is yaw control, what is pitch control, and what do you do that for. So now to know the position of this rocket, you need something to tell you. That is called gyro. This gyro and accelerometers. Gyro is all these things are in a box called inertial measurement unit. We call inertial navigation system. These are sensors packed in a thermal chamber. And there's an onboard computer. So these two give you the brain power. So what it does, IMU, it has got a position is given by a gyro and the level of acceleration is given by accelerometer. So you can see the force feedback accelerometer and the dynamic tuned gyro. These are the sensors. India was not having the best sensors because we don't make, only the Americans make best sensors. They won't give us. So we have to make it better. So this project was taken by young people who have found out how to use this core sensor to make it the best sensor. So what they did is they took the core sensor, it was given to them. They did the calibration and also they did the error modeling. Error modeling means how during the flight, during the operation of the rocket, how much error is being built because of the sensors. So they found out and they made a drift compensation software and they injected the software into that and then tried through all simulations and they put this in the INS package and embedded software is in the onboard computer. So they made a hardware loop simulation and the flight evaluation they've done. So in this process, even though we are not having the best sensors, we are getting accuracy equal to the best sensors by our genuine, the brain power of 4 young people who have found out this. So our strength lies in using the young people to do difficult tasks, where they can only do difficult tasks. So when another trajectory, you can see that one is the space trajectories go and put the required, the velocity to inject the satellite. There's another type of a rocket that is called missile. This missile is a Agni missile. If you take, it goes, it has also got stages, everything is same, but it doesn't give the velocity to go up. It takes the re-entry payload. So it goes to space about 800 kilometer altitude. Then it comes back and it re-enters. Re-enter means you know what happened to Kalpana Chawla. That high temperature zone, it comes back and you have to protect the payload. Payload is a nuclear warhead payload and then deliver it correctly to the place where you want to send it. This is attack. This is a nuclear payload attack. So this is a missile, we call it Agni. Similarly, other missile, one missile, this is BrahMos missile, where if you want to launch from a submarine, it comes from the surface, then it operates, then it immediately turns to very low altitude so that the enemy cannot find it out, and then it finish off the ship or land, anywhere it can attack. So this is called cruise trajectory. This is called ballistic trajectory. So these type of trajectories are also available. Now in the mission which we have got, which you have seen earlier, so we need to understand very important factor, what is the launch complex can do it. So you have got a launch control center, tracking station to do that mission operation. So let us understand that. Finally you have to put the satellite in the orbit. Orbit can be a low Earth orbit or orbit can be polar orbit. So what we have launched day for yesterday was the NISAR, which is put in a polar orbit. It's a satellite which can measure, which can give information about all the places on the Earth to both India as well as the NASA. That is a type of satellite. It is a synthetic aperture radar satellite, means that satellite can see through the clouds. If it is a camera satellite, camera cannot see every time. If there is a cloud, it cannot penetrate if there's a weather, rain or anything, the information will not come properly. Whereas synthetic aperture radar can give the complete detail irrespective of the surface conditions. That is a polar orbit. Then we have got geostationary orbit over the equator, 36,000 kilometers away. We put the satellite and synchronize the speed with the Earth so that one point of Earth is monitored all the time or informed. It beams to India. It beams to make us to use the satellite information all the 24 hours. These are three orbits which we are having. Now, what happens is when you transmit information, it goes to the satellite. From ground, you can transmit data. That is, you are seeing the Sun TV information you are seeing. That means Sun TV broadcasts the film, that movie, to the satellite. The satellite amplifies and it sends to many receivers which are connected to the satellite. That's why many houses can receive that information. This is called communication, link of the communication. So satellite link with the ground and transmitting the data. Okay. So this is one typical type of satellite which we have got. This is an Indian satellite called GSAT. It's a very heavy satellite, communication satellite, which has got transponders which are useful to do their communication. This communication link is established through transponders. So this is a GSLV launch and to put this satellite. Okay. This is the orbit which you have seen trajectory. It takes off, then first stage burns out, leaves the separates and goes down. Then the second stage burns. Second stage is over. Also third stage. So like the multiple stages, and finally satellite is injected and satellite operates. This is one type of trajectory which I thought I should tell you when we are talking about missile trajectory. This is satellite trajectory. When the rocket is launched, it is going up, you need the ground station to monitor it. First, you assemble the rocket and put it in a launcher, and there's a blockhouse which monitors the performance of the system. And from the control center, you give the command, countdown is done, and the rocket is launched. So once the rocket is launched, you need telemetry station to receive all the telemetry data. You need satellite information to be received, that is satellite telemetry. You need radars. These are the radars which monitors the skin mode, they can monitor, or transponder mode, it can monitor the details of the flight, where it goes, all those things. Then you have got a telecommand system. Telecommand system is, suppose the rocket is going in a particular direction, it turns and goes to the land, and it may make harm, then you destroy it. For destruction, you have got a telecommand station, which is normally not used, but in case of dangerous situation, you have to operate that. Now there's a receiving station, the computer center, which gets all the data and real time it process. Okay. So vehicle trajectory in real time you get it, which you have seen in that last time showed you. So it has gone much beyond. Then you need a radar in the different places. You need these called downrange stations. We need to get the same data you have to get. But with these data, these ground stations will not be useful when the rocket has gone much beyond. So for that purpose, we have got multiple ground stations. If you see this plot shows the dot points show there are so many launch stations in the world, or small rocket, or big rocket, big launches, or manned flight. All these things are there. We will see carefully some quickly important stations. Not all the stations we need not know. We need to know very important stations. The first one to know is the Satish Dhawan Space Center, Sriharikota. It is close to Madras, Chennai. Okay, north of Chennai. Then you have got China. It has got 4 stations, big stations it has got. Different stations it has got. Then you have got South Korea, North Korea, Japan, they have. Then China, Russia has got in the east, has got multiple stations. Russia has got. And then Israel has got a station. Okay, so these are the major stations in Asia and Europe. Then when you come to America, it has got many stations. One of them is Cape Canaveral. There is the Kennedy Space Center. It's the most important station where all the launches take place. Then the west also they have got. This is Vandenberg Air Force Station in the California. They have got. Okay, then they have got stations in Alaska, then Honolulu, that is Hawaii. They have got stations. They're not normally important. These are the important stations. This is another island. It has got Wallops Island, which is for small rockets, sounding rockets, small rockets. They use it. Like we are using Tumba, they are also using Wallops Island. Now there is one more station here. This is called French Guiana. This belongs to France. This is a very important station, the Guyana Space Center. It is in French, the most popular station. Then here you have got Australia, we have got Woolmer. Then New Zealand, they have got Rocket Labs Complex. They have got very good station. They have got this here. Let us see one by one. This is the Cape Canaveral. If you see Cape Canaveral, it is an island. Like this is the mainland of America. There is in the Florida. Then it has got a big island. There is the Indiana River flows there. So here you have got a station. This in another part, there is one more island nearby. This is called Cape Canaveral. This is the Kennedy Space Center. So it has got Kennedy Space Center and Cape Canaveral. What you see here, these launch pads, they are used for defense. These are Cape Canaveral. Kennedy Space Center is like this. They have got big assembly bay, and you can do that launch complex. You can see that here. That is here, Kennedy Space Center. We will see that. Saturn V is assembled and launched. I will show you better view. So you can see the launch complex, a big launch complex. First, where the Saturn V is assembled here, and then it goes in this one, that movable system where it is moved from the assembly tower, and it is a launch pad. So you have to be separate because the launching takes place means it's separate where it is launched. So similar launch pads are there for Atlas, Centaur, Delta. There are a number of different launch vehicles. The NASA has got all these things, but the assembly stations are also many. One of them is for the space. For the main launch vehicle called Saturn. Now they have got number of other things called for the space shuttle. Now these are used for space shuttle, and then they are running. Now space shuttle is also over. The Saturn is over. No more they are there. Now the new one is called SLS, Satellite Launch System. That is the same tower, the same assembly facility is used for that. This is a huge assembly substation, sub-assemblies here. Is a very huge one. And these are you can see the complex is very big, and it has got the different storage, propellants and all it has got. So from the final, it is taken to the launch pad. This is a launch pad where the space shuttle that what you see here is the one. And then it is locked. The movable thing is locked here. Space shuttle is there. Then the flight means man can go inside, all those things through this structure. Then launched. You are seeing more the same station, but say another part. Here they prepare the Atlas Centaur, the rocket. There's another big complex where they do that. Similarly, another complex is there for Delta. So it's a Kennedy Space Center. This is a huge one where they make all these systems preparation, assembly, and moving to the launch pad, storage of propellant. You see that there is oxygen, hydrogen storage. You will see like this. Many tanks are there. In Sriharikota also you can see the similar thing. So this is satellite assembly, satellite, and they are trying to assemble with the heat shield. One part of that, another part will come. So this is the mission control what they have got in the Kennedy Space Center. If someone goes to, one of you go to Kennedy Space Center, you can see this. The big control center they have got. This is a mission control station. And they monitor the movement of the satellite throughout the earth it moves. All the movement is monitored and then directed. Now Russia. Russia has got many complexes. One of the complex you are seeing, this is the proton vehicle, the proton launcher. So how they got a different system. They take it horizontally. They assemble horizontally the rocket and then take it horizontal, put it over the launcher and made it vertical and assemble with the umbilical connectivity and other thing they do. And then while launching, all these things will separate out, then they launch. You can see that here. First they assemble, while launching, these are separated. Only the rocket will be there vertical and it goes up. You see that they have got a launch pad. You can see that. So all these things, what they do is they take the rocket horizontally, prepare and then go to the launch pad. Here you can see the full view of the launch complex. They have got a big, the see locks LH2 storage. You can see propellant storage complex. Then it has got a launch vehicle preparation. This is a launcher. You have seen. Then before that, they have got the subsystem preparations, many places, and then do the loads. So this place is called Baikonur. This is a Baikonur. It is in Kazakhstan, where this was used as the main launch pad for Russia. But now number of launch pads are bigger. Russia is separated out from Kazakhstan. So now they have got the new stations in different places. So the new cosmodrome called Vostok, which is the one which is a bigger one now, where they launch all the cosmonauts are launched from here now. The very big rocket station now they have created in the different part of the part of Russia, eastern part of Russia. So this is the French Guyana. This is America, South America. South America, many countries are there in South America. So at Chile, this is Chile, this is Argentina. Then you got a big country called Brazil. Then like that number of countries are there. And at the top of that, there's three Guyanas are there. One Guyana is called French Guyana. That is owned by France. Similarly, there's another Guyana owned by Germany. There's another Guyana owned by UK, British. So this Guyana, French Guyana, fortunately, it is very close to the equator. You can see the equator, very close to the equator. That French Guyana. This is the French Guyana shore. This is you have got the Atlantic Ocean here. This is the Atlantic Ocean. Here, this is a long strip they have got. This is the entrance to the complex. And they have got many state things. And finally, the launch complex. So there's a mission control. You can see the mission control. And there's a big rocket they make called Ariane 5. Very big rocket. When our satellite size is very big, we go there to launch. And this is a launch complex where the same thing is assembled and launched. You can see the same thing. So assembly is done vertically, and then it is moved to the launch pad and then launched. This is the Ariane launcher. You can see the launch pad. There are tracking stations. They are also nearby. They have got. So it is taking off. The missile, the rocket is taking off. This is the French Guiana. To explain to you more clearly, you can see that big picture I have shown you. This is called Kourou. Kourou is the base. So this Guyana Space Center is in a place called Kourou. This is the station which is 5 degrees above the equator. These are the different launch complexes. You can see that. Okay. Then Japan. If you see Japan, the bottom of the Japan, for the totally bottom, you have to see, there's a Kagoshima and Tanegashima. There are two places. There are two launch complexes they have got. The bigger one is called Tanegashima launch complex, where this you are seeing here, no? Tanegashima. There are also assembly tower they have got. Then they move the tower and launch the rocket. Subsystem assembly control center, mission control center. This is Japan. They have got a rocket called H2. H2, that's also a very big rocket. Then China, if you see China has got number of stations. 4 launch complexes they have got. This is one big launch complex called Wenchang Space Launch Complex, very big one. All manned missions and all they launch from here. Very huge one, launch complex they have got. See the type of tower what they have got. Tower, that's for the assembly, rocket assembly tower. So assembled and the rocket is moved out. You see that? Rocket is moved out. First it is assembled, then rocket is moved and launched. So this is a tower which holds the rocket and with all the umbilicals, the power. But during launch, these umbilicals are removed and then launch takes place. So this is another station, Xi'an Satellite Launch Center. This is a mission control and launch from that place. So like this, they have got 4 stations. And in this is India, as you know about it, I have shown you about the Sriharikota Island, I showed you. Sriharikota Islands. You have got a mission control. You must go and see, it's a very beautiful one inside in multi-layer system. And we have got the multiple launch complexes. This is a launch pad. You can see the launch pad. So this is a launch tower and assembled. This is the LM3. That is a GSLV Mark III, which is a huge one with the 200 tons strap-ons and the liquid stage and cryogenic stage. It can carry huge weight, more than 4 tons it can carry, satellite weight. So these all like this is the 2 towers. You will see always 2 towers, one for assembly, another one is to move it, and then they do the launch. So this is a preparation, stage preparation. This is the final assembly, then it is moved out and then do the launch. So it's the big island, 40,000 acres of land, but the whole thing is in this place. All the stations are in this place. And the main control center is 8 kilometers away from this launch complex. And these are the stations. You can see the telemetry tracking stations are there. This I explained to you last time that we are launching polar launches from here around avoiding Sri Lanka, but now we are going for one more station called Kulasegarapatna, where we can launch directly to polar orbit. So these Agathiar and human space missions, you know that the preparation, you need the preparation for manned missions. These are manned mission preparation. You need to do that. This is the satellite for Agathiar, and this is manned missions, which we launched and recovered. These are all part of Gaganyaan program. So launch readiness, you see there's a small rocket called SSLV-3 or SSLV, which is a small satellite launch vehicle. This is a PSLV, This is GSLV. This is GSLV Mark 3, LM3. So these are the rockets we have got, and these are different stations for launching. And this is a preparation. Each one is prepared, how it is prepared and then taken to the final assembly that we are showing that. Just to inform you only. This is the heat shield. See the size of the heat shield? So big. We will cover that. And this is the liquid stage. We see this, you know the size of that. The heat shield and the satellite. This is also same thing, satellite and the heat shield. So we have done the moon mission also. This whole assembly is done that. See, what is required is each satellite is prepared separately in Bangalore. Our UR Rao Space Center, they make this satellite. And that satellite, once it is ready, tested, certified that it will work, then it is moved to Sriharikota. After it is moved to Sriharikota, the satellite has to be, assembled to the stage and then launched. This is a satellite, is assembled. You can see that is assembled to the bottom. That's a stage. So these preparations are done by Sriharikota. So launch vehicle preparation, VSSC is there, and we have got LPSC in Mahendragiri, where liquid stages are prepared. Solid stages are prepared at Sriharikota itself. So all these stages come one by one, they come, and then finally the assembly is done. And everything goes through all operations are done by the control center. And these are the different stations. You have got a ground station in Vietnam, you have got. So monitor because our satellite goes there, over. So it has to be monitored. You got Fiji Island. So a number of stations we have got in the world. Not only our stations, others also provide the data. And this is the Antarctica. We have got Antarctica, we have got a station. This Maitri station it belongs to India. This is near the southern side of the Antarctica, where we are doing our scientists are doing all the experiments. They stay and do the experiments. So there also we have got a station to track the satellite, because we are launching due south, so you need to get the information from the south. So what we are doing is, after the ground station, when it is launched, the satellite and ground station, they are connected. So the connection is done by the, each one's the communication system through the antenna. So you got the antenna and servo system. Then the radio frequency receive and transmit, and the baseband, that is the band is the frequency. And station computer gets all the information. But what are the things we are doing? We are doing satellite mission design and conceptualizing what type of satellite we have to launch. Then orbit dynamics, that is how the orbit should be, which orbit it should go, whether 500 kilometer or 700 kilometer in polar, or whether it should go 200 by 36,000. All is determined by the designers in the satellite control center. And then satellite network, all monitor the satellite, and satellite operations planning. That means satellite control you have to do. You are communicating to the satellite. For example, the lander has to land on the moon surface. So whole control is done from the station, ground station. You are communicating directly to the satellite. Though it is far off, you can do the communication through the command control. This is the satellite command control station. The satellite data processing. So these are the operations which are done for the satellite purpose. So for example, Nisar, which was launched 2 days back, 30th July, these are they're launched by the GSLV. And this is the satellite. You can see the huge satellite, 4,000 crore, the satellite cost. These are the satellite preparations in NASA. They do that, they assembled and they have gone to us, and we launched from the GSLV. So very important monitoring sensors are shown here. So this is a very important thing. It is connected to all the stations in the world. They will be monitoring our satellite. Apart from Sriharikota, we have got one more station. That station is only for missiles. So if you want to launch Agni, it has to have like Sriharikota, you need an island. This island is called Wheeler Island. Wheeler is the name of one British man who identified these islands. But now name is changed to Abdul Kalam Island. So this island has got all the stations, everything we have got, launch pad, everything done for the Agni. You can see Prithvi is launched, Agni is launched. We have got all the stations there, and blockhouse. Everything is there in that place. So it is from the mainland, it is 7 kilometers away, this island. So we have got the ground stations are located here, radar stations are located here, telemetry is located here, one telemetry is there also. And then the whole launch complex is in the island. This is also a big station. So you know the importance of the station is, which I have not explained to you. Let me go back to that. So you have seen many launch complexes. I have shown you Sriharikota. I have shown you 2 stations of China. I have shown you some station that Tanegashima of Japan. I have not shown you the North Korea and South Korea. Then we have shown one of these centers of Russia we have shown. Iran has got, which we have not shown. Israel has got. Then the Kennedy Space Center we have seen. And also the Guyana Space Center. Why these stations are important, you should know. Suppose you want to launch a satellite in the geostationary orbit. That means it is Earth's equator. Any satellite which is closer to the Earth equator, the equator is like this, equator, then you need minimum correction to put it in that along with the Earth's equator. This station, if you see the Guyana Space Center, which is only 5 degrees north of Guyana Space Center, you see it is very close to the equator. So it needs very, very low inclination correction. That means it has to spend less fuel. Satellite has to spend less fuel to go into the correct orbit. You understand? So this is a very important station. Suppose there is a station what America has got. This is 28 degrees. So to do correction is a large force they have to do to make it equatorial. They have to spend large force. That means the fuel is spent from the satellite. So satellite weight unnecessarily increases. Here satellite weight is advantage. Suppose we want to do a polar launch from Guyana Space Center, the French people, what they do, they launch it to the north. Straight north, this is a very clean, ocean. So they do the launch straight. So this is the best station in the world today, Guyana Space Center. That is why all the way the Europeans go to do the launch in that place. This is not a good station. Worst station is Russia, which is very north, So you need big correction you have to do. So what they are doing is, instead of equatorial plane, they do inclined launches they do because of this problem. And China, you see, is north of it. Second important station in the world, if you see, it is our station, Sriharikota, which is 13 degrees. This is 5 degrees, this is 13 degrees, this is 28 degrees, these are all for 58 degrees more. All these places are not suitable. And the Chinese have gone to the eastern end, but still they have got a problem. So if you can have a station on the equator, nothing like that. That's the best. So what we are trying to tell you is the station is important in deciding the correction required or the additional fuel you have to carry for the correction in the orbit. This is the importance of the launch complex. So now let us see. We take the mission requirement. MR is mission requirement. What is mission requirement? What type of satellite I am going to have? What is inside sensors, payloads? What it is going to do? How do I operate and maintain? This should be known first. So you have to arrive at the technical specifications of the satellite which you want to do. That is the mission definition. Then, if you know that, you have to identify the various subsystems which are required. So, roughly, you have to make a subsystem option. What type of subsystem? That is stages, propulsion, all those things. Very roughly, you decide. Then you do a trajectory analysis. The trajectory is called a 2D trajectory. If you do a simple trajectory, you know the performance of these stages to put the satellite in orbit. Then you write down the definition of various systems, the selection process. Then what do you do? Each one, you see the each one, guidance, ground station, aerodynamics and airframe, guidance, control, propulsion, payload, all these things you start defining. So this is based on the trajectory performance which you have done. From the 2D to 3D, you do that analysis. You have got roughly all estimates of the stages. Then you carry out a 6D, 6 degree of freedom model is available. Use that and then do the complete trajectory. This will include the control system required, what type of pitching you have to do. Every detail will be available in this operation called 6DOF. So that will give you a very clear idea what you have selected, whether it will do the purpose. Then you start writing the details of each one. Okay. Then you go through the simulation. What you have done, you go through the simulation. The simulation gives you the correct information, then flight prediction, then actual flight testing you do, then performance analysis. This is the system design of a rocket. To tell you more about that, so the design and development which I explained to you, it takes a lot of time. You have to develop all the systems you have to develop. Nearly 7 years we have taken to make the SLV-3, to do all the systems for rocket motors, doing a number of static tests before proving all those things. But when you go to the final operation, it's called countdown. Then also you need certain software. This is only software part. You need a launch campaign operations. You need software to check each data through the computer. Then final launch operations in 11 minutes. Then normal orbital operations you do. Then you do the post launch. Then real time operations 12 minutes. That input goes to the post operation, the flight trajectory. So this is the type. Each one has got a separate software. So here it is better for you: database, vehicle sizing, weights, propulsion, modeling, aerodynamics, trajectory optimization, performance and simulation, heat transfer analysis, structure load condition, control system design, aeroelasticity of the flexibility of the launcher, that is the launch vehicle, then control surfaces, detailed simulation, then error analysis, cost analysis, graphics, then plot. Everything you have to do. All these things are called launch vehicle design. So LAV means launch vehicle integrated design. So there's a controller which assimilates all this information and tell you whether the design is okay or not. So how do you arrive at the configuration of the launch vehicle? The vehicle configuration design, how do you do? So you need the, the whether you want to do low Earth polar or geostationary design, orbital parameters you have to decide, and then you have to do the ideal velocity requirement for achieving that altitude and orbit. The number of stages you roughly design. Then you have to go the structural factor and the specific impulse required for that each stage. Then you go through the vehicle, roughly the vehicle sizing, the propellant requirement, what type of propellant you are going to use, then structural analysis weight, then you have to motor length, diameter. So finally you get a configuration, then do the mission analysis, then preliminary system design, aerodynamic design, structural design, propulsion design, control system design. Each has got the software also. For each one, aerodynamic design, you have got a software. So similarly, structural design, all these things are software based and different types of software available for each of these design. So finally, you arrive at a vehicle configuration, launch vehicle configuration. So this once you do that, and then launch sequence you finalize, and then that you do the simulation. So how do you realize final launch here? Propulsion you have got, propulsion model you have to make a model. This is a model means not hard the physical model. It is a block diagram because we have got all the designs or they belong to a software. So software requires the modeling of the propulsion system. Then data will come from the rocket motor static test that will be integrated with the propulsion module and it goes to the digital simulation. By the time airframe, aero modeling, internal tests you have to do, all the shapes, everything we have got, we have to make the small actual models and put it through the wind tunnel. And for different speed, you have to test the and get the coefficients. So the coefficients will go into the software, the aerodynamic software. Then another one is called CFD, computational fluid dynamics, which is important to do the total analysis of the performance of the system. So all these inputs, including guidance and control, go through the digital simulation. After digital simulation, you make the hardware. You got a hardware input. Put the hardware in loop in the motion simulator. Incorporate all the guidance control, all the systems are actual systems except the propellants. You put all the systems and do the hardware loop simulation. So before hardware loop simulation, you have to finalize the avionics, then lab tests of the avionics, that is the processor, onboard computer, sensors, everything you have to go through that test. And then finally you have to go through a tower test because they are put in different height they are put. So that you have to do the test. Then actuators, sensors, autopilot, electronics, all have to go through the test, power supply. Then finally they all come to the hardware in simulation. So environment tests, vibration, temperature, all electronic systems have to go through all rigorous testing. So satellite also goes through the test, including thermal vacuum test. That is a vibration, shock, thermal cycling, and thermal vacuum test. All have to do. Once that is done, the satellite comes to the launch pad, and these are all assembled, and the rocket is made, and satellite is integrated, and then the flight test happens. All through quality assurance system, everything is checked thoroughly to make it a success. This is normally for a satellite launch. Now, if you want to go beyond the satellite, beyond the Earth, orbiting around the Earth, you want to go like the moon mission. You have seen the trajectory. This is the Apollo trajectory, Apollo missions. So Saturn was launched from the Kennedy Space Center. Then it goes around one orbit it makes around the Earth. Then it gets out of the Earth's gravity, goes in a long trajectory to the moon's orbit, where the Earth and moon, equal force happens, that gravity. There it is pushed to the orbit of the moon. Then it orbits around the moon. Then finally circularized, goes very near 100-kilometer orbit. It is there for a long time. And then you separate out and go and land. Once landing is done, the people have to come back. The manned mission means they have to come back, they have to come back. So there's a propulsion module in the lander which fires, goes into the orbit, and there's a, the orbiting platform will be there, which will be the dock with the orbiting platform. And the orbiting platform goes around the moon and then gets out of the moon's orbit, goes here, comes and lands in the ocean. These all landing is on the ocean for the Apollo mission. So here it takes only 4 days to reach this moon. From the launch to the landing, only 4 days. But what we have done, Chandrayaan-2 and Chandrayaan-3 missions, what we have done, we have got a launcher Mark 3, GSLV Mark 3. It cannot carry directly to the moon. Compared to Saturn, is small. So what we have to do? We have to raise the orbit. So we have put the satellite. Using the satellite fuel, you have to go through first it was launched to 170 by 40,000 kilometers. Is the orbit. Launch vehicle work is over. Now satellite takes over. The satellite is orbiting. Then you go and inject the fuel here. It goes to higher orbit. Again inject the fuel, goes to a higher orbit. Like that, you go on doing it to raise the apogee of this is called apogee of the satellite. Then finally it goes to a very big orbit, very high elliptical orbit, from 200 to 4 lakh kilometers it goes. And then once it goes there, then you transfer it to the moon's orbit. Again it goes into a very big elliptical orbit and finally come to 100 by 100, and then you go through the landing. Okay. This was Chandrayaan-2 mission. Third mission also the same thing, it happened. So that's how the launching takes place. You have seen, you know about it, you have seen it in the TV you have seen. So Chandrayaan-2, there was a problem. It lander failed because of the soft landing was not possible. The thruster did not give the required thrust to limit the speed. So it went and impacted on the ground. So in the next Chandrayaan-3, we did the correction, and we also put a lot of factor of safety to do that. The 30-kilometer to landing, that one we have done it very carefully. We have done a lot of simulations have been carried out, and the software has been corrected to make the land successfully. We landed, and India is the only country which has landed in the southern side of the moon. So if you want to go to the, to Mars, it's not easy. The distance is more. So there's 3 types of phases involved for Mars. So geocentric phase, that is the Earth, it is centered around the Earth. Then heliocentric, that is the sun centered. And then Martian phase. 3 phases are involved. So first you go around, this is the you should know when you are launching where it is the Mars. So Mars at the time of launch is here. Mars at the time of landing is here. So Mars has got an orbit. It goes around the sun. Earth has got an orbit. This is the Earth orbit. So Earth's position at the time of launch is here. Earth's position at the time of at the arrival time at the Mars is Earth is here. So you have to calculate this very carefully and then transmit from the Earth orbit to Mars orbit. We did the same thing, orbit, the raising we have done for Mars also. We did it and then we put it here to the final. It landed. Not landed, it over the Mars, it orbited. So this shows the details of that. how you get into the Mars. The gravity between Earth and Mars is very, very important. So you can see Mars orbit, you did the same thing, 250 by 23,000 initially, rise the orbit, go to that orbit, and then go to the Mars orbit, correct it, and then go around, go to a circular orbit outwards. This is a Mars or satellite. Different payloads, it has given very good information about the Mars. So 225 million kilometers of satellite has moved. See that? Distance between Earth and Mars is 225 million kilometers. The whole satellite has to go and but 225 kilometers is straight, but it has to make so many orbits it has to make. That means it would have moved 1,000 million kilometers would have gone. So in all these things, you should understand one thing, which is how the takes place, how the whole thing, how it takes place. You have got a fuel. There was a question. That's why I'm answering this. The fuel is getting reduced when the rocket is going up. Okay. Total rocket mass M changes as the fuel is burned. When the fuel is burnt, rocket weight changes. The mass changes. The propellant is burnt at the rate of M. That is called M dot. Okay. Now let us see what happens. So it is M dot into the velocity C. So momentum dm by dt by C. Dm by dt, the mass variation into C. And F is equal to ma. So m into dv by dt. That is velocity. A velocity divided by time is acceleration. So m dv by dt is force. This is a normal formula. The thrust calculation is m dot into C. So m dot is the flow rate at the velocity which you have got for the vehicle. So this is called dm. M dot is dm by dt. Time-wise, how the mass varies. So now both are equal, right? So you put dm dv by dt is equal to dm by dt. Direction is different because thrust. Poles, thrust. Okay, opposite direction. So if you look at this, dt cancels. So dv is equal to minus c dm by m. What is dv? The differential velocity. What is the purpose of this rocket, this stage? To give a velocity, dv. So the dv is a very, very important factor for the stage. That is the velocity it finally gives. Incremental velocity it gives, added velocity it gives for the rocket. So that is calculated like this. So how do you know the C? C is the velocity, exhaust velocity. M in kilogram, effective exhaust velocity C in meters per second, mass flow rate is kg per second, that is m dot, thrust is equal to F, calculated in newtons, using Newton's second law of force, law of motion. So this is the important calculation which you should know. Rocket, how do you calculate the differential velocity which it gives is the velocity of the rocket divided by into dm by m. So this based on this is the rocket equation. This is the only equation for the rocket which was written by Tisiolsky. This whole formula came from Tisiolsky when he said rocket will take man to the Mars. So delta V is equal to VE. V is the exhaust velocity, dV is the incremental velocity, log of m0 to mf. Mf is the total mass, final mass, and the initial mass is m naught. So another important factor which you should know is the specific impulse. Velocity, you know, specific impulse you should know. So this I have told you, when you go for solid or liquid, the velocity is 300 units. The same thing when it goes to cryogenic, it is 450. Ramjet gives you 600. Liquid ramjet goes to 1200. So in the last propulsion we have seen, liquid ramjet in BrahMos It is 1204 times better than solid. So if you want more, you have to go to scramjet, which gives 3000 units. That is using liquid hydrogen, you can do that. So all the space vehicles in future, what ISRO will be launching, will be scramjet based on liquid hydrogen. That will have very high specific impulse. So now specific impulse also to be calculated. How do you calculate the specific impulse? That is from the rocket equation. So when you see in the thrust is equal to m dot v. Okay, this is the exhaust thrust which is coming out of the divergence. But you take this. Okay. So m dot v is the thrust. So then from that m dot v, you have to calculate m dot v equivalent. You have to find out. V equivalent is including this. So forget about that now for the time being. So this F into T is the total impulse. The force operated during the time F into T is equal to the I. I is the total impulse. I is equal to mv equivalent. So when you integrate m dot, you get m dot d m v equivalent. So ISV is equal to velocity divided by g naught. Simple equation. So ISV is equal to force divided by m dot g naught. M dot g 0, that is the gravity. M dot is the flow rate. Force, flow rate, You take this force is equal to m dot VE. If you put m dot cancelled, VE finally comes. So the net answer is, for the calculating the specific impulse, is V equivalent divided by G naught. So that is specific impulse. Specific impulse is a measure of the efficiency of the rocket engine. The change of momentum per unit mass of rocket fuel. Simply put, specific impulse is a measure of how much push accumulates as you burn the fuel. So if you know that, there's a movie on that, this one, I will just show.
This video is sponsored by Squarespace. Stay tuned to the end to find out. Not as hard as its point in the sky at all times. In other words, you can leave your satellite dish that receives your favorite TV. What this means is that the satellite appears stationary compared to the rotation of the Earth. It stays in the same point in the sky at all times. In other words, you can leave your satellite dish that receives your favorite TV shows in one position and never have to change it. So the question is, how do scientists calculate where to put the satellite so that it remains at the same point in space? Orbital mechanics is rooted in Kepler's laws of planetary motion, published way back in 1609. Newton's laws of universal gravitation, published in the Principia Mathematica around 1687, also plays a role in many calculations. Kepler's laws allow us to calculate the period and speed of such a satellite. Speed is the square root of mu over r, where mu is the standard gravitational parameter, equal to Newton's gravitational constant times the mass of the planet. R is the radius of the satellite from the center of the Earth, and the period has the following formula. Note that the speed and period only depends on the radius of the satellite, not on its mass. A geostationary orbit is circular, and since the altitude of the satellite does not change, its speed must be constant. If you do the calculations, you will find that the geostationary orbit is 35,786 kilometers from the equator. The orbital period is 23.93 hours, or 23 hours and 56 minutes. You might say, why isn't it exactly 24 hours? Well, 23 hours and 56 minutes is actually equal to one sidereal day. This is the time it actually takes for the Earth to complete one rotation with respect to a non-rotating frame of reference. The reason we normally count 24 hours as being one day is because 24 hours is the precise time that the sun is at the same spot in the sky every day. But you have to keep in mind that the Earth moves with respect to the sun. The Earth moves 1/365th of an arc around the sun during this time. That's about 4 minutes. In other words, the Earth has to rotate just a little bit more, about 4 minutes, before the sun is directly overhead. But one full rotation around its axis is actually 4 minutes less than that. Now the question is, how is a communication satellite inserted into an orbit? The first step in this process is to launch the satellite on a rocket that has the payload capacity to carry the satellite to this orbit and can impart the speed necessary to maintain this orbit. In the United States, one workhorse rocket for this task has been the Atlas V. This rocket weighs about 700,000 pounds or 317,000 kilograms at launch and can lift 28,000 pounds or 12,700 kilograms to geostationary orbit. 90% of its weight is fuel, which is typical for rockets. The main engine is powered by liquid oxygen and RP1, which is a highly refined form of kerosene, similar to jet fuel. How does a rocket work? First, a rocket does not rely on the atmosphere to oxidize the fuel like a jet engine does. That's because it carries its own oxidizer. This allows it to be able to function in outer space where there is no atmosphere available. A jet engine would not work here because there's no oxygen available to burn the fuel. Rocket engines are an application of Newton's third law. For every action, there's an equal and opposite reaction. The combustion of fuel causes high-pressure exhaust gases to be expelled at supersonic speeds. The rearward acceleration of this mass of the fuel leaving the rocket nozzle causes an equal and opposite reaction of forward thrust powering the rocket forward or upward during launch. The shape of the nozzle of the rocket is designed to increase the velocity of the exhaust gases further to increase its thrust. Highest thrust is achieved when the mass flow rate of the fuel and exit velocity of the propellant is high according to this equation. The fuel has to be delivered at high volume and pressure to get the thrust required for lift. This pressure is powered by fuel pumps that boost the pressure of the gases before entering the combustion chamber. Because these pumps can boost the pressure, the fuels do not have to be pressurized so high, and the thickness of their storage tanks can be reduced, resulting in weight savings and increased payload capacity. Now you might ask, how are these pumps driven? They're typically driven by using a small amount of fuel to drive a turbine which drives the pump. Now maintaining a stable straight flight is an issue. Early rockets were stabilized by large fins. For stable flight, the center of pressure where the net aerodynamic force acts must be lower than the center of gravity. This is because if its angle of attack changes relative to its flight path, the net force acting below the center of gravity can restore the stability that realigns the nose of the rocket. Modern rockets don't use fins though because of the extra weight and aerodynamic drag that they cause. Stability comes from swiveling the thrust nozzle to keep it stable. This is called gimbaled thrust. A geosynchronous orbit is achieved in stages. Typically, the rocket will take the satellite to its orbital altitude, but the initial orbit is elliptical. This elliptical orbit has to be changed to a circular orbit to become geostationary. So for example, an elliptical orbit may take the satellite to an altitude of 150 kilometers at its lowest point called the perigee, and to the geostationary orbit of 35,786 kilometers at its highest altitude, the apogee. We can use Kepler's laws to calculate the speeds it will have at these points, about 36,500 kilometers per hour at the perigee and 5,800 kilometers per hour at the apogee. The laws of physics are such that the satellite continues on an elliptical orbit until something changes its orbit. This change is done by accelerating the rocket at precisely the right time during its trajectory so that it forms a more and more circular orbit with every pass around the Earth. The thrusters have to be turned on precisely at the apogee to accelerate the craft from 5,800 kilometers per hour to 11,000 kilometers per hour, which is the speed it needs to have to maintain a circular geostationary orbit. As you can probably surmise, there's only one geostationary orbit, and it is at 35,786 kilometers above the Earth's equator. There's no other geostationary orbit, and there are 500 satellites at that altitude. This real estate, even in space, is limited. The total perimeter available is about 265,000 kilometers. This launched from Cape Canaveral, Florida, which is located. But the advantage is that these satellites are cheaper to launch and cheaper to make because they don't have to be as powerful, since transmission distances are a lot shorter. So what happens now? that we finally have our satellite in orbit around the Earth. We have adjusted to make it a circular geostationary orbit. We have placed it in a correct slot assigned by the ITU, and we have adjusted its angle of orbit so that it is at the same plane as the equator. The first thing that happens is that the solar panels are deployed so that the satellite can have power to function. The main function do the same task. These satellites usually have at least 2 antennas, which may be aimed at 2 different apps, listen to Sirius XM radio, going to have an internet presence, create a website regardless of their technical ability. They are known to have... This video is sponsored by Squarespace. Stay tuned to the end.
Okay, thank you. So this video summarized most of the things which I talked. Okay? Shall we discuss questions?
Yes, sir.
Hello. Sir, my name is Sheikh Adil from 9th Standard Belamal Metric, sir. Sir, you said that missiles are launched generally in Abdul Kalam Island, and Sriharikota is normally used for rocket launching, sir. Why is this happening, sir?
One is belonging to ISRO. They do that launching from ISRO center. Other one belongs to DRDO, which is in charge of missiles.
Oh, okay, sir. I also have another doubt. Sir, you said that French Guiana is a very popular rocket launching station and it is the best station because it is close to the equator. Why is it better to launch rockets near the equator, sir?
Inclination, I explained to you, when you launch, there is an inclination to the equator. Okay, that inclination should be minimum. Then you need minimum force to correct it. So the fuel which has to carry it by the satellite will be less if it is closer to the equator.
Okay, sir. Thank you so much, sir.
Right, thank you.
Sir,
Speak.
sir, myself, Niragan from St. Anthony Matriculation High Secondary School, sir. Sir, how do rocket designers balance the need for payload capacity with the need for fuel efficiency, sir?
Payload capacity?
Sir, how the rocket designers balance the need for payload capacity with the need for fuel efficiency, sir?
So fuel which has to be carried by the satellite depends on the correction required to be done and also to the station keeping. If you are going to operate for say 10 years the satellite, there will be drift in between. So the fuel is required to correct that drift. So as long as the fuel is there, the satellite will be usable. Suppose the fuel is not there and if there's a drift, you cannot correct it, means satellite will not be useful to you. That is calculated, how much required to be used for station correction, orbit correction, all these things are calculated and that much fuel is taken.
Okay, sir.
Hello, sir. Myself, Atish Weber from Sai Matriculation Higher Secondary School, Madipakam. Sir, my doubt is, in your previous session, you said about BrahMos missile uses liquid ramjet. So during extreme maneuvers, is there any chance liquid inside the missile get pushed in one side, which creates a problem in fuel injection?
No, nothing.
Why is it, sir?
Nothing. No, fuel is used to inject into the combustion chamber, and you draw the air to ram it, and then they burn. You get the required, the force required combustion.
Okay, sir. Sir, and I have another doubt, sir. Sir, in SLV mission slide, you talked about self-destruction options in satellites. So my question is, does the satellites carry some explosive to detonate itself? Or
No. Not the satellite, launch vehicle. See, satellite has gone to the orbit, no problem. What is required is while launching, you are launching it with the assumption that it will go in a particular trajectory to put the satellite. And suppose this trajectory is not being followed. It is going in the wrong direction. Suppose we launch from Sriharikota, it comes to Chennai, assume.
Yes, sir.
It comes to Chennai. Chennai people, your school will not be there. So we have to protect your school. So we do that destruction.
Okay, sir. Thank you, sir.
Thank you.
Sir, I am S. Adhavan from Chara Metropolitan Higher Secondary School, Tirumundi, sir. Sir, my question is about August missile, sir. Sir, how does August missile solid fuel system compare to the liquid fuel alternative, sir?
Solid ramjet is 600. Liquid ramjet is 1200. Just now I showed to you. That's
Yes, thank you, sir.
ISP curve I showed you, no? There's a difference. Liquid ramjet is more powerful.
Okay, sir. Okay, sir.
Hello,
Thank you,
sir.
Ah.
Myself, Agathiar from Velamal Matriculation High Secondary School. So my doubt is, once again, sir, what is the differences between Satish Dhawan Space Center and the upcoming space ports like Kulasekharapatinam?
You people don't listen properly, I think. See, when you launch the polar orbit, if you have to go to the South Pole, you are launching in a direction not to harm the Sri Lanka. Because if you launch straight from Sriharikota, it will go over Sri Lanka. So you have to do a dog-leg maneuver. You have to go around and then launch. Because of that, we are losing weight of the satellite. Performance goes down. So in Kulasekharapatinam means Sri Lanka does not come into the picture. You do direct launch. I showed you that curve, the one inclined curve, then one straight launch. Did you see that?
Yes, sir.
Then why you are asking this question? Huh? You have not followed that. Okay, next question.
Sir,
my name is Savitasra. I am studying 8th standard, Gundu Subaya Pillai, T. Nagar Girls Higher Secondary School, sir. Sir, I ask one doubt, sir. What is the reason for splitting each part to go up at the rocket?
Splitting which part? Splitting each stage?
Yes, sir.
You are talking about why you have to split each stage, you are saying.
Rocket, sir.
Rocket, see, when a rocket has got number of stages. Hello?
Yes, sir.
Hello.
Yes, sir.
When I showed you the rocket, first when I showed you a diagram, then I said this is a solid rocket, this is a liquid stage, this is cryogenic stage. I showed you, no?
Yes, sir.
You are asking why like that? Your question is why you have to do like that, you are saying. Is it your question? Or different parts you are saying? What is that question? Speak.
Sir.
What is the question?
Splitting the stage.
Splitting the space. Which space?
Rocket splitting, sir.
Not splitting. We are not splitting the rocket. It has got stages.
Okay, sir.
You are written wrongly your question. Somebody has told you wrongly. Your father told you wrong question. Check with him.
Okay, sir.
Sir, good evening, sir. Sir, I'm Yasun Vishayada from KSR School, sir. Sir, I had a doubt that why Rocket Lab of New Zealand is complex, sir.
Why Rocket Club of New Zealand? New Zealand.
Yes, sir. Is complex, sir.
Complex, I did not say.
No, sir, I saw in that notes, sir.
No, launch complex. Complex means it's a system. Not complex means not in the your meaning. Complex is many systems are there in one place. It's called complex.
Okay, sir.
There are two meanings of complex. One is, oh, it is very complex, I don't know. That is one complex. Another complex is a group of things put together is called complex. That's
Okay,
called
sir.
launch complex.
Okay, sir.
Okay, another question.
So another one question, sir. Why Satish Dhawan Space Station is located in island of Sriharikota in India?
Why it is chosen Sriharikota?
Yes, sir.
Why we have chosen Sriharikota as the launch station? Is it? That's the question.
Yes, sir.
You need. So suppose you want to launch. Will you launch east or will you launch west? Which is the right thing to do? Answer. Answer. We want to launch a rocket. You will you launch east or will you launch west? Which direction?
Sir,
Huh?
East, sir.
Why?
So because of the velocity, sir.
Velocity of what?
Uh,
Don't know.
yes, sir.
Earth rotates, isn't it? Is
Rotation of the Earth, sir.
Earth rotates or it is stationary?
Okay, sir.
Huh? Is it Earth rotating or Earth is stationary? What is your answer?
Earth is rotating, sir.
Rotating in which direction?
East, sir. East direction, sir.
So west to east, the Earth is rotating. So if you launch the rocket in the east, you are taking advantage of that rotation. Okay? Understood?
Okay, sir.
So
Yes, sir.
that means if you are having a big launcher, which is to carry the satellite, you should find a launch station in the west. Number one.
Okay.
Number two, the launch station should be in the east, right? Number two, in the eastern coast, if you see in India, you see where are the islands? Why island? It should be separated from the mainland for safety. You launch it explodes. Assume whole launcher explodes. People will die. So you
Yes,
need
sir.
a place which is away from the main land. So you need an island. So they have surveyed various islands in the east and found there's a large piece called Sriharikota, which is 40,000 acres available. Suppose you are Sarabhai. Okay? Assume you are
Okay, sir.
which will you select or not?
Sir?
Will you select that Sriharikota, which has got 40,000 acres
Yes, sir.
and it is island?
Yes, sir.
Now you know the reason?
Yes, sir.
Okay, thank you.
Thank you, sir.
Good evening, sir. I am a Fidos Khan, studying in 8th standard, Sairam Matriculation Higher Secondary School from Chennai. My doubt is how a rocket knows I want to reach in space in this destination. Like Chandrayaan 3, I want to launch in moon only. How the rocket knows, sir?
I have shown you how the rocket Chandrayaan trajectory is, how it goes around. I explained it in detail. I explained to you.
Yes, sir.
Hmm.
But how the rocket is landing in a particular place, what we aim for?
That you have to calculate particular place. You know the place where it goes, what is the velocity required, what is the type of trajectory you should take. Everything is to be calculated. That is the rocket science. It is not simple. It is to be done by the group of people. They will calculate, how many circles you have to make around the Earth to reach that orbit near the moon. Then how do you transfer to the moon's orbit? What will be the moon's orbit at that point? Then how to make it small circular orbit? How to land it? Everything is calculated by proper software. It is done. That if you want to know how it is done by the group of people, it will take 5 years for you.
Thank you, sir.
You are only in the 8th standard.
Yes, sir.
So it is all done by people. Calculation.
Good evening.
Good
evening, sir.
You join ISRO after you grow, then you will find out. Okay, next.
Good evening, sir. I'm Prajwal Sanju from grade 8B, sir, Bales Global School, Mokapet, Chennai, sir. Sir, I have a doubt, sir. You said that all the missiles are launched from Wheeler Island, sir.
Okay.
Sir, if a war is going on in Pakistan or China, if we launch a missile from the Wheeler Island,
that is testing.
It needs to
Wheeler
go from
Island,
there
we are
to the
testing.
war field, sir.
Hello, we are proving the rocket. For proving the rocket, proving the missile, you need a place. That's called the range. It is not the war. War, we will use it in the border only. This is only for testing, to proving it.
Okay, sir.
Okay. For
Sir, I have
Pakistan,
another
you
doubt,
cannot
sir.
launch from Wheeler Island, you cannot launch it to Pakistan. Okay, next.
Okay, sir. Sir, what will happen if you said that satellite needs to go in a circular orbit for in the GSL orbit, sir? What will happen if it is an elliptical orbit?
It will go in elliptical orbit if you want it. It all depends on what you want. What orbit you want, it will go. Okay, next question.
Good evening, sir. Okay, sir. Sir, I have another doubt, sir.
No, over. Next, Jaydev.
Sir, good evening, sir. My name is Jaydev, class 8 from Bellamar Bodhi campus, Anupanadi, Madurai.
The voice is cutting, I say. Talk properly.
Sir, you mentioned that the scientists were monitorized the rocket after its launch, sir. Sir, my doubt is that what the scientists will do if the rocket haven't fought, they calculated it after its launch, sir, to safeguard the satellite, sir.
No, there are correction methods inside the launch vehicle. If a launcher is going, launch vehicle is moving, each stage is when it is imparting velocity, it goes in a particular trajectory. If the trajectory is different, it is alleviating, there are correction controls are there in the launch vehicle itself. But if there is a failure, if it is going in a different trajectory, then the satellite will not be put in the correct place. It's a failure.
Okay, sir.
Okay.
Good evening, sir.
Thank you, sir.
Okay.
Good evening, sir.
Ask the question.
Good evening, sir. I am Elfasira from Sairam Institution, sir. I have a question. Nisar, what propulsion, sir? Solid or liquid?
Nisar has come, lot of information has come in the internet about Nisar. Please go through the internet. Okay?
Okay, thank you, sir.
Rahul?
Sir, good evening, sir.
Okay. Sanjay
Sir, my name...
Sanjay Kumar, you asked the question already.
No, sir. I am asking it now only, sir.
Okay.
Sir, you have explained about the concept of BrahMos missile and how it works, no, sir? Like how it takes off from the cruise and goes on to destroy a target, no, sir?
Myself, Agathiar from Velamal International School.
Sir, in that case, what is a 0G pushover, sir? 0G pushover, sir.
0G
pushover, sir. It was mentioned in the BrahMos missile trajectory, sir.
No. But there's no 0G.
Yes, sir. 0G.
G is gravity.
Yes, sir.
It's not, there's no 0G comes in. 0G is in the vacuum. There's no 0G.
Okay, sir. And why a separate telecommand is used for a self-destruct sequences, sir?
That is if it deviates. If it deviates and it's going to make harm to the people, then you have to destroy it.
Okay, sir.
Okay, there if it deviates, automatically it does. That is called self-destruction.
Okay, sir. Sir, we know that the ionosphere actually reflects the waves, sir, and the ionosphere is located about from 50 to 1,000 kilometers in altitude, sir. And how can geostationary satellites can communicate with Earth if the ionosphere is reflecting radio waves, sir?
See, these are all radio frequency can penetrate anywhere. There's no such thing. A command, RF command, if you give to a satellite, it will work. So the satellite is linked by different means of frequency. We call it RF, we call URF, you call ultra frequency, you call it in S band, you call it P band. So many bands are there. Frequencies are different. This is nothing to do with your ionosphere.
Okay, sir. Thank you, sir. Thank you very much, sir.
Okay, next. Velamal Vidyalaya.
Sir, myself Kalai Selvan from Velamal Vidyashram School, sir.
Okay.
You said that Chandrayaan-3 satellite was landed on the southern part of the moon. What kind of a difficulty it faces, sir? Other country and all, they do not landed that such satellite, no, sir, on that south pole.
This is not called a satellite. What is satellite? Satellite is the one which orbits. What is the definition of satellite? Any object which is moving around the Earth is a satellite. Yes, moon is a satellite of the Earth, but that is natural satellite. If it is if you are putting a satellite like the NISAR you put or GSAT if you put, which is orbiting around the Earth, it is called artificial satellite. Okay. When something is landing on the moon, it's called lander. It's called lander. Okay. The lander in Chandrayaan-2, the lander did not get the sufficient thrust upward, so that soft landing was not possible. In this Chandrayaan-3, it was trajectory was corrected, software was corrected, thrusters were properly designed, simulated, and then they launched it to the right place.
Okay, sir.
Okay.
Okay, thank you, sir.
Thank you. Any more question? Time is going to be 8 o'clock. Any more question?
Sir, my name is Shrita and I'm 8th standard studying in Agathiar school.
How do scientists accurately calculate and adjust a rocket's trajectory during its flight, especially considering variables like atmospheric drag, gravitational force, and celestial bodies and fuel consumption, sir?
That is the design of the launch vehicle. You take into account all these points. Gravitational force, all celestial bodies, debris hitting, so many things are there. All things are considered while designing the rocket. Okay. Satellite has nothing to do with the rocket. Satellite is put in the orbit by the rocket. Afterwards, satellite takes over.
Thank you, sir.
So one more question. I want to finish it now.
Sir, myself Harini from St. John's Metric High Secondary School, sir. And I have this question. Sir, Harini from St. John's Metric High Secondary School, sir.
Yeah.
Sir, why does a rocket launched from Earth to Moon need a much higher thrust-to-weight ratio in its first stage? But a lander lifting off from the Moon or Mars can have significantly lower thrust-to-weight and yet still escapes their gravity, sir.
The rocket which you are launching is against the gravity initially.
Okay, sir. Yes, sir.
So if you are asked to go to a distance of 4 lakh kilometer, travel, push it to the satellite, you have to impart a big velocity to the satellite.
Okay, sir.
If you have to give big velocity to the satellite, the power of the rocket should be very high. Thrust should be high to take it. That is why if you see the Saturn is a very big launch vehicle. Okay?
Yes, sir.
How much thrust is generating, I have explained in one of the classes. So our rocket is a small rocket, it cannot give that one. There's a difference. So that is why you need a bigger rocket, which we don't have. That is number one. Number two, the movement of the Chandrayaan moon lander has nothing to do with gravity. It is above gravity. So there's no gravity there. Once you put it into the final orbit around the moon, afterwards its operations are based on the moon. Moon has no atmosphere. Moon has no, it has got its own gravity only, which is 1/6 of the Earth's gravity. So you have to
Yes,
take into account only that while landing the lander.
okay, sir.
That's what we calculate and then we put it. We do the trajectory.
Okay, sir. Okay, sir.
Okay.
Okay, sir. Thank you, sir.
So my name is Srinita.
Balamurian.
Yes, sir. Yes, sir. Yes, sir.
So you have to close it. It's 8 o'clock. I have got some other work.
Yes, sir. Yeah, you can, I'll close it, sir. Thank you so much, sir. Thank you so much for your time. Students, we understand your enthusiasm, so we will be continuing it by tomorrow. So you can write up your questions and keep it right away. And by tomorrow, once the class is over, you can go ahead and post your questions. So thank you so much for your time, sir. Thank you, sir.
Okay, thank you.
Students, you please be there, and coordinators, you also be there. So we just want to share some thought process. So please be waiting for our instructions. Once sir has left, we will be having it. Coordinators, how many coordinators are there? So coordinator Sai Saravanan, coordinator Kalei Rani, and anyone, please lower your hands, students. So no more questions is allowed right away. So who is that Jaguar? So today we just want to give some instructions that everyone has some discipline procedures. So if at all you are not adhering with the principles, you won't be allowed to attend the classes, as well as you won't be having the rights management to question sir also. So your questions won't be answered there. You need to maintain your discipline. So we are going on putting up these things because Pillai sir is a person who has given such a things, and he wanted to give back to the society. In that case, he's sitting here for more than 2 hours to teach you, as well as answer whatever you are about to raise as a question. So in such case, we need to have the salutation to him rather than putting up a bad face, that you are putting up your school name in a dark also, as well as your discipline procedure is also it has been blemished. So please ensure that you follow the instructions whatever been given by your coordinator. Yes,
Hello,
sir.
sir. You can stop the live here. Live you can stop.
Okay. Kabilan, please stop the
Okay, sir.
Kabilan,
stop.
you can talk.
Okay. So how many of them don't have the